In this video, we're going to present an example of the principle of virtual work applied to a continuum. The purpose of the example is just to explain what the various terms that appear in the equation mean. In this example, we have the Cauchy stress distribution in a plate given by the following matrix. Sigma on 1 is equal to x1, x2, sigma on 2 is equal to sigma 2, 1 is equal to 5, and sigma 2, 2 is equal to x1, where x1 and x2 are the coordinates inside the plate. First, we need to find the equilibrium body forces vector. Then, we need to find the traction forces on the boundary edges A, B, C, and D, edge A, edge B, edge C, and edge D. And finally, we need to verify the principle of virtual work. The principle of virtual work implies that there is a virtual displacement, so we want to verify the principle of virtual work, that the external virtual work is equal to the internal virtual work, when a virtual displacement field with a horizontal component u1 star is equal to ax1 plus bx2, where a and b are constants. So, to find the equilibrium body forces, we apply the equilibrium equations, and as shown previously, rho b1 is equal to negative partial sigma 1 by partial x1 minus partial sigma 2 1 by partial x2 minus partial sigma 3 1 by partial x3. If we take the derivatives of these components, you get that rho b1 is equal to negative x2, rho b2 is 0, and rho b3 is equal to 0. In order to find the traction vectors on the boundary, we need the normal vectors to the boundaries. Boundary A has normal vector NA. NA has components 1, 0, so this is the vector NA. NB, which is the normal vector to edge B, has components 0, 1. So this is the normal vector to edge B. Edge C has normal vector NC, where NC is equal to negative 1, 0. And finally, edge D has normal vector 0, negative 1, where this is the direction of the vector perpendicular to the edge D. The traction vector on each edge is equal to the stress matrix multiplied by the corresponding normal vector to that edge, taking into consideration that a particular edge has certain coordinates that are known. For example, edge A, the traction vector on edge A is equal to sigma transpose multiplied by the normal vector NA. Edge A has the variable x1, the coordinate x1 is always equal to 2. So TA is equal to sigma transpose NA when x1 is equal to 2. The traction vector on B is equal to sigma transpose NB, and this is calculated when the coordinate x2 on edge B is always equal to 1. Similarly, the traction vector on edge C is equal to sigma transpose NC, evaluated when x1 is equal to 0. And finally, sigma transpose ND gives me the traction vector on edge D when x2 is equal to 0. Doing these multiplications, we get TA is equal to the vector 2x to 5, the traction vector on B is equal to 5x1, the traction vector on C is equal to 0, negative 5, and the traction vector on D is equal to negative 5, negative x1. In order to verify the principle of virtual work, first we write the virtual displacement. The virtual displacement field is equal to the horizontal component is ax1 plus bx2, and the vertical component is 0. The associated virtual strain is equal to half the gradient of u star plus the gradient of u star transpose. This is equal to the matrix with components A, 0, b over 2, and b over 2 in the off-diagonal components. The rest is straightforward. The equation of the virtual work states the internal virtual work has to be equal to the external virtual work. So let's calculate the internal virtual work. The internal virtual work is equal to the stresses multiplied by the corresponding virtual strains. It's equal to the summation, each component of the stress multiplied by the corresponding component of the strain, all integrated over the whole plate. The plate has dimensions 2 in the component x1, 1 in the component x2, and thickness of T, so in the direction of x3. So, each component of the stress multiplied by the corresponding component of the strain, we get the first component of the stress is x1, x2 multiplied by A, and the second component is 0 multiplied by x1 gives me 0, and then finally b over 2 multiplied by 5 and another b over 2 multiplied by 5. So that gives me 5b plus ax1 x2. Integrated from 0 to 2, 0 to 1, 0 to t on dx1, dx2, and dx3 gives me a plus 10bt. So this is the equation of the internal virtual work, and this is the value of the internal virtual work obtained. The external virtual work has 5 components. A component due to the body forces, a component due to the traction vector on edge A, a component due to the traction vector on edge B, due to the traction vector on edge C, and finally due to the traction vector on edge D. The one due to the body forces is obtained by integrating the work done by the body forces over the whole volume. So this is obtained by integrating the value of the body forces, rho b1, multiplied by the horizontal component u star 1, plus rho b2 multiplied by the virtual displacement component u star 2, and so on. But we only have u star 1 that's not 0, and so we multiply rho b1, which we obtained previously, multiplied by u1 star. So we get this equation integrated over the whole volume. We get negative 1 over 3, 3a plus 2b multiplied by t. On each edge, the external virtual work is calculated by multiplying the traction vector on that edge multiplied by the displacement of that edge. So for edge A, the traction vector is TA and the displacement is u star evaluated at that particular edge. At that edge, the coordinate x1 is always equal to 2 on edge A. And so by evaluating this, we get 2x2 plus 2a plus bx2. This is the value of TA dot the virtual displacement when x1 is equal to 2. And this is integrated over the edge. The edge has variable x2 and x3, and so x2 is integrated from 0 to 1, and x3 is integrated from 0 to t. Doing this integration, we get this value, 2 multiplied by a plus b over 3 multiplied by t. Similarly, the external virtual work on edge B, this is edge B, this is the force acting on that edge. The displacement of that edge is u star evaluated on that edge. On that edge, x2 is equal to 1. And so doing that dot product gives me the work done by the external stresses TB evaluated over the whole surface. The surface has x1 varies from 0 to 2 and x3 varies from 0 to t. So integrating this over the surface gives me this value 10 multiplied by a plus bet. Similarly, the external virtual work of the forces acting on edge C can be obtained by integrating the stresses dot the displacement of that edge, which is the displacement evaluated at x1 equals 0. When we substitute, we'll get that this product is equal to 0, so this integral is equal to 0. Finally, the external virtual work on edge D is equal to the integration of td dot u star, where td is the traction vector on edge D, and u star of edge D, the displacement of this edge, is the displacement field evaluated when x2 is equal to 0. By doing this calculation, we get negative 5a x1, and by doing the integration on x1 and x3, x1 varies from 0 to 2, x3 varies from 0 to t, we get negative 10at. The external virtual work is equal to the sum of the external virtual work of all the forces applied on the plate. So the external forces are the body forces, and the forces on edge A, edge B, edge C, and edge D. By summing all these values, we get the external virtual work, which is the external virtual work due to body forces, edge A, edge B, edge C, and edge D. By doing a summation, we get A plus 10B, all multiplied by T, which happens to be equal exactly to the internal virtual work.